All right, so here is an example of a one sample t-test. And notice this particular example is telling you to use the p-value method and as well as to use the t-test. And it even tells you that you're doing a one-tail test. So, it does give you some guidance here to, what realm you're working in. Before I get into this specific problem, I kind of want to set up and continue what I was discussing in the last video on the one sample z-test for a mean. And so let's take a look at this scenario here. Very similar to what we have over here. We have a new battery that supposedly lasts longer. Okay, and that's what the company is claiming. And so based on your experience, they know the regular batteries were 30. And so what they're looking for here is looking for an increase in the batteries for continuous use to last longer than the average to be higher than 30 hours. Now, how much higher than that is, this isn't going to give us that information. The confidence interval can, and that gets into a little bit more detailed analysis, but we're going to say anything more than 30 is better than 30. And whether it's practical or not, that's the whole debatable thing. But that's what we use estimation or confidence interval for to follow up on this. So anyway, what we do is we take 15 batteries. We found that they lasted 33.9 hours, and the standard deviation was 9.8. And based on what we talked about last time, said we were going to use this normal density to find the p-value. What we're lacking here is the population standard deviation. And this is more realistic, right? Because if they come up with new batteries and the mean changes, is the standard deviation going to change? And so we can't always assume it's going to be the same as it was in the previous, measurement or population, so to speak, because we're dealing with the population of old batteries here and the population of new batteries. So what happens is, if we go to use the sampling distribution, we're kind of stuck, right? We know S, we don't know sigma, but really, when you think about it, this is an estimate of this. And so there's this fellow, William Gossett, who was a brewer at Guinness back in the, you can see his lifespan there in the late 1800s, early 1900s. And he devised well, he was a kind of a closet statistician, so to speak. He published works with statistics, and this was one of his works, the T distribution and the T statistic, but he did it under the pen name of student. And the reason he did that was he didn't want a conflict of interest being an employee of Guinness. He wanted to be somewhat anonymous or remain anonymous there. So he went ahead and did that. And so that's why we call it the T statistic, I guess, because S is already used for something else. So they're using the next letter T in the name student. So, he was kind of a, like I said, a closet statistician, so to speak, but he devised this method, and it's really kind of common sense, but he provided all the mathematics. I'll show you here in a second, essentially what he did, but this sigma, replacing this with S, could we still use the normal density? We could, but the problem is that this is going to change from sample to sample, right? One sample we might get 9.8 hours. Another one we saw in that simulation that I showed you last time, the next sample might be 35 hours, and this sample standard deviation might be something like, I don't know, 10 or 8 or something like that. That's going to be different. So now we've got this varying as well. So what his solution was to come up with a new group of, and I say group of densities, and they were called the T densities. So if you look at this one here, this red line is the standard normal, right? It centers at 0, standard deviation is 1, and so forth. But if you look at the blue one here, or the purple or the light blue one, and the blue and purple are pretty close here, I don't know, top of one another. But you notice there's a little more area in the tails, so we say they're kind of like fatter tails. And it's kind of shorter in the middle here. These are shorter because the area of any probability model has to add up to be 1. So if the tail area increases, then obviously the middle is going to get less in there. And you can see that I plotted here these, and what this is actually called a degree of freedom. And basically, without getting into all the nuts and bolts of it, essentially the degrees of freedom are going to be the size of the sample minus 1, or n minus 1. So this, I had a slider here I was dragging around for the degrees of freedom. So this would be actually 2. So that's right on top of that one here. So the purple and blue are literally right on top of one another here. But I could have, this software here, this is a screenshot of Fathom. It doesn't run on my Mac, and it's older, so I can't demonstrate this live for you. But what you would do is, what you see happening is the degrees of freedom increase. Okay, the tails get a little bit, like this blue one here has 5, get a little bit shorter, or skinnier, so to speak. And so what we see is this trend that a t distribution becomes a lot like a z distribution as the degrees of freedom increase, which is a result of the sample sizes increase. Okay, so I guess another way of saying that is if we have super big samples, it's okay to use the z probability model, but for these problems and in practice we typically use the t test. So you're going to be required to do that, even though these probabilities might not differ all that much, as far as the p-values. All right, so that's basically it. Is why we're using the t-test. We're going to calculate the statistic very similar. We're just using this basically the same formula, other than using the sample standard deviation in place of the population standard deviation. Okay, but that's going to give us a different probability, but it's just going to be as easy to find on your spreadsheet as in some of the other softwares it was with your others. So you're going to feel like we're doing the same thing here. Okay, so all right, so this scenario here is a manufacturing process that has a completion time of 65 minutes. So that is the historic one, or the one they're claiming. Or assuming it's true, the old method, however you want to word that. So we're going to go ahead and enter in u equals 65. And if we go down here, it says it's claimed that due to improvements in the process, that mean completion time is going to be now less than 65. So that tells us that we're using a one-tail test where we're saying that it's going to be less than the null. And it says up here to use the t statistic, but if it didn't have that, and I'm not sure what your homework assignment looks like, it may not have that heading or guide you as much, but we're missing the population standard deviation. So that tells us that we have to use the t for that. Okay, and you'll see this degrees of freedom. It's going to be the sample size minus 1. So we have a sample of 12 times, so that's going to be 11, but you'll see your spreadsheet does do this automatically for you. And we want to find the value of the test statistic and the p-value, and go ahead here whether to reject or not to reject. Okay, so let's jump into your spreadsheet to do that. So I'm going to go back here. I'm going to go to the master sheet, and let me go to the t template. All right, and we're coming over here as significance. Here's the confidence interval, and we are using this one here. All right, so our X bar, since my memory is not what it should be, I believe we said that that was 59 and 11. Okay, so we've got a 59. We got 11 for the standard deviation. I think we had 12 of these things, and I'll go back to get the significance level, and significance level was 0.10. Okay, and oh, I forgot to put in the null too, so that's 65. Okay, so 0.10, that's already in there. Okay, so we see we have a test statistic here now of 1.889. So if we round out the 3 decimal places, that's going to give us 1 negative 1.890. Okay, so let me go ahead and put that in. Got it already? Let me slide this over so I don't look at that at the same time. Okay. Negative 1.890. So I need an 8 there. Okay. And the p-value here, now this is kind of nice because they give you the left and right tails. Remember, your Z test did not do that. It only gave you the right tail. So that was kind of an issue. So if you didn't look at that video and you're running into problems here, you may want to look at it. I addressed this issue over here about it not giving two tails. But okay, so go back to this. I am just reading this stuff here and filling in the blanks. So my p-value for my left tail test is going to be 0.043. Okay, and let's see, I rounded that correctly. So, all right, so our p-value is definitely less than the alpha, right, which is 0.10 up here. Okay, so can I conclude the mean completion time using the process is less than that? Yes, I'm rejecting, right? Since the p-value is less, I'm rejecting and going with this, and that's what I'm referring to down here. So I'm going to answer that with yes. And that's all you need to do, okay? I will go ahead and check this just to be double sure. And I am hold up to my custom of not including the 0 in front of the decimal point here, okay? So I'm pretty consistent with that. I just kind of wanted to show you here, you have some options to kind of double check because obviously your spreadsheet here doesn't have a graphic, right? So if I would go and type in that negative 1.890 into the, if I go back here to the t-distribution, and just to show you this, the degrees of freedom, I think what was the sample size again? That was 12, right? Yeah. Oh, and by the way, here's your degrees of freedom, right? It just pops up for you. So, if you put 12 in here, it's going to give 11 here. Just, you don't have to memorize that, but you'll probably get used to doing that. So anyway, all right, so I want to go back to my t-distribution here. So I want 11 degrees of freedom. And I want the area to the left of a value, and I think that was negative 1.890. Okay, put the labels on the plot. So there's your p-value there. And so that's what you get. Okay. So again, you see it's very similar to the normal curve. It centers at 0 and so forth. This tail is going to be a little bit fatter than the standard normal. So if I had a Z statistic, right, a negative 1.89, that p-value is actually going to be a little bit lower because the normal tail is going to be a little bit shorter, okay, or skinnier, if you will. All right. So that's one way of getting that. Another way of getting that p-value is to use this calculator here. And so, if I did, find the, well, that's not the right one here, the probability of t, it's being less than that. So you kind of got to do, let me clear all this out of here again. So what I'm going to do, this finds the area to the right of that. So if I would take 1 minus the probability of t being to the right of negative 1.89. Okay, with 11 degrees of freedom. Okay, you can see that we're getting the same p-value here of 0.0427 as well. Okay. So this is kind of set up to just do right tails where staplets, you have the ability to go left and right. And obviously, I think probably the more direct way of doing it is, provided you understand, is just looking at the output here to get, on your spreadsheet. Okay. So that is that is an example of one in which we would find the p-value. Okay, so if I jump back here in ALEKS, and I want to give you one using the critical value. Okay, so you'll have to do one of those. And like I said, I did do one for the Z, but it's very similar. Okay, so let me do this. So let's jump into this one here. It says, scenario here. You always want to orient yourself here. So excuse my reading, but you can stop it and read it if you want the video. Thanks to an initiative to recruit top students, the administrator of the college claims this year's entering class must have greater mean IQ scores than that of the previous years. So, they go ahead and they test, randomly select 21 people here, and they found that the mean is 115 and the standard deviation of 10. Okay, so that's for my sample, and then the previous year was 113. So setting this up, obviously we're going to do the same deal here. We want to have the old one, which is mu equals the 113. And also, we want this one to be greater than, so I am going to come down here and select mu greater than 113. All right, and we're using RT statistic. Now, this one here, it wants to find the value of that statistic for the rejection region. So in other words, I want to find the t statistic with a p-value of 0.05. That's essentially what I'm doing here, okay? And how I do that is, there's a couple of ways we can do this. One is, on your calculator, and your spreadsheet's going to do this. I'll show you how to do it, but this is kind of a neat way of doing this is you type this in here, and if I, can scroll up here, we got a random sample so of 21. So I've got 20 degrees of freedom. And if I want the area to the right to be 0.05, sometimes these are to the left. I can't remember. We'll find out here real quick. Yes, I just put the area to the right of 0.05, which is 1.725. Okay, to 3 decimal places. All right, so I'm going to put 1.725 here. Okay. No, that's my critical value, 1.725. Okay. All right, so let me X this out so I don't do here or confuse you. Okay. And degrees of freedom are 20. And so let's see if we can get all this stuff out of our spreadsheet here, because that critical value is just the one thing here that we need. And we're going to make our decision based on our test statistic relative to the critical value. Okay. So, you can find that critical value doing this, or let's jump into your spreadsheet here. So I'm going to come over here and let me place all this over here so it's a little easier to read, so I don't have to go back and forth. So our X bar, I believe, was 115. So I'll type that in. Our hypothesized value was 113. Our sample standard deviation, I forgot that already. That was 10. Okay. So I'm going to change this to 10. Oh. If I can change it back here, I don't think I did. No. Okay. So that's 10, and my sample size here was 21. That's 21. All right, and my alpha was what was it? 0.05. It doesn't really matter here, but I just want to show you the p-value. Yeah, 0.05. All right. So anyway, here it gives you your degrees of freedom. Here it's given us our p-values here of a left side, right side. This is clearly a right-sided test. Okay, so it gives us a p-value of 0.18. Okay, but the big thing here we need is our t-statistic, right, which is 0.917. 917, if I round to 3 decimal places, looks like I did that. Okay, so now since it's a right test, this is less than that. Okay, now if it was beyond that, and I'll give you a graphic here in a second, but if it was beyond this, okay, then what I would say is that I would reject it because my p-value would be less than 0.05, okay, which is what we had over here for our alpha. So the idea is this, if my t-statistic was this, it'd be 0.05. It was to the right of this, which would be greater than that, it would be less than 0.05, I would reject. But since it's to the left of it, that means the p-value is actually more than the 0.05. Okay, so you have to kind of get in the idea that if this were my test statistic, my p-value would be exactly 0.05. Well, it's less than that, so it means it's going to be greater than that. Okay, so I would fail to reject this. So this right here stated is the alternative, right? We're saying that these IQ scores are greater than 113. So we cannot conclude that. So we would actually select no there. Okay. So again, we go ahead and check our results and we got everything correct. And of course, I forgot the 0 in front of the die. I'm just going to keep doing that. So I'm going to ignore that, quit talking about it. But anyway, that's how you do this one. Okay. So one more, quick little thing here with the, to show you this idea with the critical value of what's going on here is that, if at 1.725, so if I quickly get into my t distribution and if I go to the right of a value, 1.75, and my degrees of freedom have to be 20 here. Okay. So if I calculate that area, there's the 0.05, right? So, if I went back and did the test statistic, okay, so that's what I've said, you have to pretend that, okay, if that was my t statistic, that's the critical value here, my p-value would be 0.05, but it wasn't, it was 0.917. So if I change this now to 0.197, I can tell you my t statistic is going to be right about here, right? So that area to the left or to the right of this is going to be much bigger than 0.05, okay, which it is, it's 0.18. And by the way, they give that to you on your spreadsheet there. So so you can see here that this is just a visual of why I would not reject that, okay? Because my test statistic right here is not beyond the other one, 1.725, I think it was, which had a p-value of 0.05. Okay, so I hope this little bit extra helps here. It's not that you have to go through and do that every time, but hopefully it's going to help you kind of understand what's going on right here. The other thing I said was, well, you could use your, where's the the 1.725 come from? Where does this critical value come from? Well, the other place that we can get it is on here. And given the area, find the t statistic. If we would say the area, tail area right here is 0.05, and we put in 20 degrees of freedom, that would be mean there here, 0.05, out of there. Here is your 1.725. Okay, so this little section right here did the same thing as this ALEKS calculator did over here. I'll just show you this real quick, just so you can see it's the same thing. Okay, and you're getting the same number over here. Okay, so you obviously have this, this needs to be addressed in terms of, the course expectations and everything, but, you have some additional things you can maybe cross-reference with or, verify. All right. So there's your there are your two examples of the t-test. One of them was using the p-value method. The other one was using the critical value method. So what I'm going to do is come back with one more video here showing how we test for population standard deviation and variance, and using the chi-squared statistic to do that. I addressed the, like I said, the type 1 and type 2 errors. So if you didn't look at the last video, which was on the one sample z-test, I did talk about the type 1 and type 2 errors in there as well. So, so that's it for this video, and I'll be back with the next one here.